Hey everyone, my name is Dong Yu. I'm from the Physics Department of UC Davis, and Professor Adam Mo has just given a talk, a wonderful talk about organic solar cells. So my talk will be focused on inorganic nanostructure solar cells. Just start with a very brief introduction about nanocrystals. So it is well known that bulk semiconductors are, the energy states in bulk semiconductors are continuous. They have conduction band and valence band. And in atoms, the energy states are discrete. Well, the nanocrystals usually composed of hundreds to thousands of atoms, and they bridge the electron structures of bulk and atoms. So they still have band gap like this, but within the band, the energy states are actually discrete. And remarkably, when you change the size of the nanocrystals, the energy spacings between different energy states will be changed. If you increase, if you decrease the size, then energy spacing will become larger. So because of this size tunability of the band gap, the nanocrystals have basically they can change colors. Even the same materials, if you change the size, then the band gap will be different, so its color will be different. So this size tunability has attracted attentions for using nanocrystals as materials for solar cells, because you can basically change the band gap to match the solar spectrum, so it can maximize the efficiency. So although it has been tried, many groups have tried to use nanostructures to make solar cells, the efficiency so far is still low. The overall power conversion efficiency is still only a few percent, much smaller than the conventional silicon solar cells. So it is crucial to understand what's going on, the mechanism of the nanostructure solar cells. So there are many things that we don't quite understand because this is relatively new. So I think some of the important things include, first, the electronic structures and carrier dynamics of the quantum confined semiconductors is not well understood. As I said, when you shrink the semiconductors to a very small size, the electron holes will be confined, so their electronic structure will be totally different from the bulk. And to understand the fine electronic structure is important, especially it's very important to understand the carrier dynamics, basically how the carriers inside the band will decay, how the hot carriers will decay to the band edge carriers. If it's slow, then maybe instead of generating phonons, it may generate multiple isotons, so you can increase the efficiency. The second important point is to understand if you want to use nanocrystals, you need to not only need to separate the charges, but also to take the charges out. Then the charge carrier needs to transport through nanocrystal thin films. So it's also important to understand how charge transport in the nanocrystal thin films. The nanocrystals also has a very large surface to volume ratio, so it has a very large surface. So you may have a lot of surface effects. You may have surface states which may contribute to the recombination. So if electron holes recombine before they are separated, then you lose energy, you lose efficiency. And the last is when the electrons and hole pairs are separated, the charge carriers still need to be taken out. So it still needs to transfer from nanostructures into the electrodes. So you may have a contact barrier between the electrodes and the nanostructures, which can also take away some efficiency. So to improve the overall efficiency of the nanostructure solar cells, you will understand all of them is a really complicated system. They're including many subtypes. So my talk will mainly focus on the charge transport, surface effect, and contact barriers. So this is outline. So I will tell you first about such transport in nanocrystal thin films. So nanocrystals can be made in solution. So if you mix the cadmium and selenium precursor together, you can make cadmium cyanide nanocrystals. And the blossom spectrum shows that the band gap can be changed when you change the size. And nanocrystals actually are usually kept with some organic ligands to prevent them from aggregation and to maintain the solubility. However, the cadmium ligands, those pairs, they also cause problems because it makes the conductance very low. It makes the nanocrystal thin films very insulating. So resistivity is reported to be 10 to the 14 ohm centimeter. So you can make it more conductive by taking away some of those ligands and replace them with shorter ones. So, but the nanocrystal is still not very conductive because they are usually intrinsic. So you need to put in charges into the conduction band, and then it will be more conductive. It turns out that the conventional backgate methods are not very successful in nanocrystals, and electrochemical methods turns out to be more successful. And indeed, when you inject electrons by applying electrochemical potential to your nanocrystal thin films, you were able to see this spectrum change. You can see that the interband is bleached because this transition is not allowed anymore if you put the electrons into the conduction band, and also you can see this interband absorption induced by the extra electron in the quantum dots. And our main purpose to do this is to study the conductance. So here there's a cartoon. So in the beginning, we haven't turned the electrochemical potential. All the valence band is filled and conduction band is empty. So it's basically intrinsic semiconductors. So it has a very low conductance. So this current is conduction current, corresponds to this solid line. So we are here. Then we turn up the electrochemical potential that basically corresponds to raising the Fermi level. So we can see as the Fermi level reaches the first excited state in the conduction band, and electrons can come through, and we got some conductance. But if we increase the Fermi energy a little bit more, then we feel all these first excited states. Just because energy states inside quantum dots are discrete, there is energy spacing between the first excited state and second excited state. So after we fill in all this, the valence doesn't increase anymore. Actually dips a little bit until you reach the Fermi level again. Then it becomes more conductive because we are reaching to the second excited state. So after this, we basically freeze the electrochemical cells, so all the electrolyte solution is frozen. So electrons inside the quantum crystal have nowhere to go, so the electron will remain there and film stays conductive. So we can do the low temperature measurement and to study the transport mechanism of the electrons in the film. So this is the conductance versus the temperature plot. If we plot in the normal way, log G versus 1 over T is actually non-linear. Only when we plot log G versus 1 over square root T, it's pretty linear, so it actually follows this equation very well. So the conductance is exponential with 1 over square root T. So this can be explained very well by a variable range hopping model, which considers the hopping of electrons from quantum dots not to the nearest neighbor, however to the quantum dots far away from the nearest neighbor. And this hopping distance actually depends on the temperature. And so some more data, so we change the bias and measure conductance, and also at different temperatures. The theory goes well with the experiment. And this is a different system, not cadmium cyanide anymore, but like cyanide, it also follows this variable ring hopping model. And if we apply a magnetic field, then basically it also follows this model because the magnetic field basically is squeeze the wave function of the electrons inside the quantum dots. So the conductance decreases when you apply an external magnetic field. Okay, so this is summary of the first part. So the conductance of quantum dot arrays can be enhanced by replacing the organic ligands with shorter ones, and also electronic transport in quantum dot